All right, let's talk about a really powerful strategic idea, thinking in reverse. It's a way to win games where you have to figure out what your opponent is going to do at the very end, before you even make your first move.
Okay, put yourself in this situation. It's a classic. You're a small startup, the challenger, and you're staring down a giant that basically owns the whole market. Your decision seems simple, but the stakes, they're massive. Do you go for it and compete, or do you play it safe and just stay out?
So let's map this out. You can think of it like a decision tree. The very first move, the first branch in the tree, belongs to you, the challenger. You have two choices, go in or stay out. Pretty straightforward so far.
But here's the thing, it's a sequential game. Your move isn't the end of the story. If you decide to go in, the ball is suddenly in the incumbent's court. They see you've just stepped onto their turf, and now they have to make a choice. They can either acquiesce, accept the new competition and share the market, or they can fight you, maybe with a nasty price war.
Now let's put some numbers on this to make it real. These are the payoffs. Just remember, the first number is for the challenger, that's you, and the second is for the incumbent. And higher is always better. So if you stay out, you get a safe but small payoff of 1, and the giant keeps its nice, comfortable 2. If you go in and they acquiesce, you hit the jackpot. You get a 2, they get a 1. But if you go in and they decide to fight, well, that's a disaster for everyone. You both get 0. So, to figure out what's likely to happen here, game theorists use a really famous tool called a Nash equilibrium. You can think of it as a no-regrets point in the game. It's an outcome where, once everything is said and done, neither player looks back and says, "Man, I wish I'd done something different."
And this is where it gets really interesting. When you run the numbers, you don't find one Nash equilibrium, you find 2. The first one makes total sense. You, the challenger, enter the market, and the incumbent agrees to share. Everyone's happy. But the second one? It's a real head-scratcher. The challenger stays out because the incumbent is threatening to fight. How can that be a stable outcome?
So let's really dig into that. Why on earth would this outcome, out-fight, be considered an equilibrium? Well, it all comes down to a tiny but crucial detail in how we define a strategy.
You see, in game theory, a strategy isn't just your initial plan. It's a complete contingency plan. It's a full rulebook that says what you will do in every possible situation that could ever come up. And that right there is the key. If the challenger truly believes the incumbent's complete strategy is, if you enter, I will fight no matter what, then what's the challenger's best move? It's to stay out, right? Staying out gets them a payoff of 1. Going in would mean a fight and a payoff of 0. So, given that threat, the challenger has no regrets about staying on the sidelines.
But this brings us to the million-dollar question, which the source material puts so perfectly. The incumbent can shout from the rooftops that it's going to fight, but is that threat actually credible? When push really comes to shove, would they follow through?
This whole puzzle really shines a light on a little flaw in the standard Nash equilibrium, at least when it comes to games that play out over time. It allows for threats that seem, well, kind of irrational. Threats a player would never actually carry out. We need a sharper tool for the job.
To get to that sharper tool, we first have to understand the idea of a subgame. And it's simple, really. A subgame is just a smaller piece of the main game that starts from any decision point. So, in our example, once the challenger decides to go in, the next part of the game, where the incumbent chooses to acquiesce or fight, is its own little subgame.
And that brings us to the hero of our story, Subgame Perfect Equilibrium, or SPE. It's a genius idea. An SPE is a plan that doesn't just work at the start of the game. It has to be a Nash equilibrium in every single subgame along the way. Its whole purpose is to weed out those empty, non-credible threats.
Okay, that sounds great, but how do we actually find it? Well, the method is surprisingly elegant, and it's incredibly powerful. It's something called backward induction. The logic is as simple as it is brilliant. You think in reverse. You start at the very end of the game, the final possible decision, and you work your way backward. At every step, you figure out the only rational choice a player could make, and you basically prune away all the other irrational possibilities from your decision tree.
So, let's try it. We go to the end of our game. The challenger has already entered. Now, the incumbent is at the final decision point. They look at their options: acquiesce and get a payoff of 1, or fight and get a payoff of 0.
And right here, the whole puzzle just unravels. When the moment of truth actually arrives, any rational incumbent is always going to choose to acquiesce. Why? Because 1 is better than 0.
The threat to fight was just talk. It wasn't credible. So we can just snip that fight branch right off our tree. It was never a real possibility.
Okay, now we take one step back in time, to the very beginning, back to the challenger's initial decision. But now, the challenger is playing with perfect information. They know that if they enter the market, the rational incumbent will choose to acquiesce.
So, look at the challenger's choice now. It's not a risky gamble anymore, is it? It's a simple, clear-cut comparison. Stay out and get a payoff of 1. Or go in, knowing for a fact that the incumbent will share the market and get a guaranteed payoff of 2.
And just like that, the puzzle is solved. By thinking backward, we found the one and only subgame perfect equilibrium. The single rational path is for the challenger to enter and for the incumbent to acquiesce. That confusing, non-credible threat has completely vanished.
So what are the big takeaways here? First, be careful with Nash equilibrium in games that unfold over time. It can sometimes lead you down a weird path. The real lesson, though, for business, strategy, anything, is that a threat is totally useless if it isn't credible. To find the real solution, we use subgame perfect equilibrium because it demands that everyone acts rationally at every single step, and the way we find it is with that amazing tool, backward induction. You always have to start from the end.
And that leaves us with one final, really provocative thought. We just spent all this time showing how an empty threat is doomed to fail. But what if you could make that threat credible? Imagine an army that, to prove it would fight to the death, literally burned the only bridge it could use to retreat. Knowing what we now know about credible threats, when might it actually be the smartest possible move to burn your own bridges? Think about that one.